Hello everyone, welcome to Vyas Edification. In this session, we are going to discuss class 11 chapter number 8 Gravitation and Exercise Solutions. Clear? And in this session, you will find detailed solution of each and every question, as well as through the question you will find some key concept of a theory. Clear? So definitely you will enjoy this session. So concentrate on a screen. We are going to start. Let's ready. Now student, we are going to discuss question number 8.1, and in this question it is given to you. Answer the following. Clear? Number A part. You can shield a charge from electric forces by putting it inside a hollow conductor. Clear? So this is very clear to us. Let's suppose I am taking here a hollow conductor. So let's suppose this is a hollow conductor. I am drawing here, this is a hollow conductor. Let's suppose I am placing here a charge inside this hollow conductor. Now we know very well, if we are talking about a hollow conducting shell or hollow conducting sphere, at that time we can see electric field, this is inside this hollow conductor we have 0. Clear to you? So electric field inside this conductor we have 0. Clear? So electric field we have 0 now, but it is given, can we shield a body from gravitational influence of nearby matter by putting it inside a hollow sphere or by some other means? Clear? So let's suppose now I am saying here, let's suppose if I am placing here a M mass body. Clear? And this M mass body is actually we place here M mass body, and let's suppose we place this M mass body in a hollow sphere. Clear? Now let's suppose here we have another body having mass capital M. Clear? So now we are saying that here electrostatic force is actually, electrostatic field inside is 0. So we can say here we can protect this charge from electric forces, that is from the surrounding electric forces. Clear? But now we can say actually if we are placing this smaller mass in a hollow cylinder or hollow sphere, or you can take any body. Clear? You can say gravitational force always act. Gravitational force always act along the line of joining like this. Clear? So it means we can say here we cannot shield any body from, if we are placing that body in any object. Clear? So now we can say no, we cannot shield a body from gravitational influence of nearby matter by putting it inside a hollow sphere or by some other means. Clear? So our answer is here, that is no. Clear to everyone? Now listen carefully. Yes. Now we are going to discuss part number B, and in this part it is given to you, an astronaut inside a small spaceship orbiting around Earth cannot detect gravity. Clear? Let's suppose an astronaut, we have an astronaut is actually in a satellite. Clear? Or we can in a small spaceship, in a small spaceship astronaut is actually having some motion. Clear? But let's suppose if I am saying, if the size of that spaceship, or we can say size of the space station, now we are making it large. At the time we can say if astronaut is moving inside this spaceship, at the time we can say it can actually feel some variation in acceleration due to gravity. Clear? So definitely we can say at the time that astronaut, it may feel some, we can say some gravity. Clear to you? So a very simple conclusion we have. Yes, if size of a spaceship is very large, at the time it is a possibility that an astronaut can feel variation of acceleration due to gravity. Clear? So this is all about part number B. Now it is given in a part number C. If you compare the gravitational force on the Earth due to Sun and then due to Moon, you will find that the Sun pull is greater than that of Moon's pull. Clear? So now actually if we talk about Newton's law of gravitation between first Sun and the Earth, and second we are observing this Newton's law of gravitation between Sun, we can say Moon and Earth. Clear? So if I write here ratio, I can say gravitational force between Sun and Earth, and we can say gravitational force between Moon and Earth, this ratio is given by G m1 m2 upon r square. So I am writing here, this is ms I can say ME over, I can say distance from between sun and earth. Clear? This is RS square multiply, I can say here this is RM square divided by this is MM multiply, I can say this is mass of earth. Clear? So I can say this one and this one cancelled out. So from here we can write like this, MS over MM multiply, we can say this is RM divided by RS and this is whole square. Clear? Now you know what is mass of a sun. Clear? We can directly say this is 2 into 10 to the power 30. 2 into 10 to the power 30 kg is a mass. We can say this is solar mass. Clear? And mass of a moon, we know this is 7.3 into 10 to the power 22 kg. Clear? Now if we talk about distance between moon and earth, so distance from moon we have 3.8 into 10 to the power 8 meter. Clear? And square divided by what is distance between sun and earth, it is given to you 1.5 into 10 to the power 11 whole square. Clear to you? Now we do not need here an exact calculation. Clear? So if you do here some approximate calculation, you can say here, yes, you can say here just if we calculate power of a 10. Clear? This is 10 to the power 30, I can say this is 10 to the power 8, this one we have 10 to the power 16 and this one we have 10 to the power 22. Clear? So 16 and 8 we can say 10 to the power 24 and this one we have 10 to the power 22. It means we can say whatever value we will get, we will write here 10 to the power 2. Clear? Yes or no? Because this is 10 to the power 16, this is 24 and this one we have that is 10 to the power we can say 22. Clear? So directly we can say whatever value we will find here, this will be multiplied with 10 to the power 2. Clear? Now we can also write like this. Let's suppose I am saying this is 2 multiply, I can say let's suppose this is 4. So 4 multiply 4, 16, 16 multiply 2. I can say this is 32 divided by this is 1.5. So we can say 2.25 and it is multiplied, let's suppose 7. So 7 multiply 2.25. Clear? So from here you can calculate, you can write like this, this is 1/4 of 7. 1/4 of 7 we have 3.5 or we can say 1.75. So 1.75 plus 14, that is 15.75. So whatever we can see here, we are getting this value approximately equal to 2 into 10 to the power 2. Clear? It means we can say here that gravitational force acting between sun and earth, it is 2 into 10 to the power 2 times of gravitational force acting between moon and earth. Clear? So definitely we can say gravitational pull due to sun, it is more compared to gravitational pull due to moon. Clear? So this is all about first part of a question number C. Clear? Now it is also given here the tidal effect of moon's pull is greater than tidal effect of sun. Why? Clear? So now let us try to understand this statement. Now actually it is generally seen if we are talking about tidal effect, or we can say TIDAL. So if I am talking about this effect, I can say this is actually inversely proportional to cube of distance between two planets. Clear? So from here we can say if I am talking about, clear, if I am talking about TM, it means tidal effect due to moon and this is sun, we can write like this, this is equal to RS over we can say RM and this value we have cube. Clear? So definitely we can say here we have value 1.5 into 10 to the power 11 divided by, we can say this is 3.8, so 3.8 into 10 to the power 8. Clear? Whole cube. Now you can say this value we have approximately 1/2. Clear? Or you can say this is 10 to the power 3 and 10 to the power 3 multiplied power 3, it means this will become 10 to the power 27. Clear? It means directly we can say this tidal effect of this moon, it will be more compared to tidal effect of sun. Clear? So definitely we can say gravitational pull due to sun is more compared to moon, but if we are talking about tidal effect, so definitely tidal effect is more due to moon compared to sun. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.2, and in this question again we have 4 parts A, B, C and D. Clear? And now we have to check here that which one we have a correct alternative. Clear? So first we are going to discuss here part number A. So concentrate on a screen. Acceleration due to gravity increases or decreases with increasing altitude. Clear? So now we can say, if I am talking about acceleration due to gravity. Clear? So let's suppose initial I am assuming we have a earth, and let's suppose we are placing any object at a surface of a earth. Clear? Now what I am doing here, actually I am now lifting this object from a surface of a earth to a certain height. Clear? And I am actually assuming here, let's suppose I am saying the height that is very less compared to radius of earth. Clear? Just I am assuming. Clear? At that time I can say this G dash, this is given by G1 minus 2h upon Re. Clear? You can also write a general expression like this, that acceleration due to gravity due to variation of a height, this is given by G1 upon 1 plus h upon Re. Clear? And we can say this is whole square. Clear to you? Yes. Clear? So from here you can say, if we are increasing height, clear, statement is given to you, acceleration due to gravity with increasing altitude. So we can say when h is increasing, it means this factor is increasing. When we are subtracting from 1, it means definitely this factor is decreasing. So I can say acceleration due to gravity decreases. Clear? You can also see here, if we are increasing here h, definitely denominator increases. When denominator is increases, it means I can say this value of G dash decreases. Clear? So what is the correct option we have? Correct option here we have, that is acceleration due to gravity decreases with increasing altitude. Clear to everyone? Now if I am talking about part number B, in part number B it is given to you acceleration due to gravity with increasing depth. Clear? So now you know definitely that acceleration due to gravity due to increasing depth, this expression is given by G1 minus d by Re. Clear? Where we are taking this d from surface of a earth. Clear? You can say like this. Let's suppose here we have this earth. Clear? Let's suppose this is initial position. I am taking this body at a certain depth d. Let's suppose this is center O. Clear? Here we have radius Re. Clear? So at this position, if I want to find what is value of acceleration due to gravity, I can say this is given by G1 minus d by Re. Clear? So now we can say as d is increasing, it means I can say depth is increasing. Clear? So when depth is increasing, it means I can say this acceleration due to gravity decreases. Clear? So acceleration due to gravity, I can say this decreases with increasing depth. Clear? And actually we are taking here an important assumption that we are taking that density of this earth is uniform. Clear? Actually this formula is derived whenever we are assuming density of a earth that is uniform. Clear? Okay, fine, complete. Now if I am talking about part number C, in part number C it is given acceleration due to gravity is independent of mass of earth or mass of a body. Now listen carefully. Actually we know force of gravitation, this is given by G me m upon r square. Clear? Where me is what? This is mass of a earth, and small m is what? Mass of a body. Clear? And r is what? It is distance between small m mass and mass of a earth. Clear? Now, or you can say r is a distance between a particular body and we can say earth. Clear? Now if we can also write like this, let's suppose here we have this is earth, we are taking here mass me. Let's suppose here we have another planet, we can say another planet or satellite, any object. So and let's suppose it is having mass m and distance is given to you r. Clear? Now let's suppose I want to find what is acceleration due to gravity act here. Clear? So definitely we can say this object is actually revolving around the earth, so a centrifugal force will act towards center along radius, and actually that should be equal to G me m upon r square. Clear? So we can say we can write here this value we are having mg. Clear? So I can say we can write like this mg, this should be equal to G me m upon r square. Clear? From here we can say m and m, this one is cancelled out. Clear? So now we can write like this value of g, this is given by G me divided by we can say r square. Clear? Now from this expression we can observe that acceleration due to gravity is depending only on a planet through which we are actually observing that gravitational pull. Clear? It means we can say that acceleration due to gravity, it does not depends on the mass of an object that is revolving around any object. Clear? It means directly I can say what is the correct answer of part number C. Acceleration due to gravity is independent of mass of, I can say, mass of body. Clear to everyone? Yes. Now we are going to discuss last part of this question. According to this part, the formula minus gmm 1 upon r2 minus 1 upon r1 is more or less accurate than formula mg r2 minus r1. Actually, this formula is given to you for change in potential energy. Clear? Actually, we know change in potential energy is given by u final minus u initial. Directly you can say this is mg r2 minus r1. Clear? But actually, if we are talking about accuracy of a formula, according to me, I can say this formula is more accurate. This formula is more accurate. Why? Because we can say final, this can be written like the GMEM upon let's suppose RF minus, I can say this is plus GMEM divided by R initial. Clear? Now we can say this formula is more accurate compared to this one. Why? Let's suppose an object is going at a certain height from the surface of earth. Let's suppose an object is going at a certain depth from the surface. Clear? At that time we will find there is a variation in acceleration due to gravity. Clear? So now we can say at a different location we will find variation in this value of g. It means I can say definitely there is a change in potential energy we will find. Clear? So according to me, I can say this formula is more accurate compared to this formula. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 8.3, and in this question it is given to you, suppose there existed a planet that went around the sun twice as fast as the earth. Clear? So in this question it is given to you, let's suppose we are assuming, let's suppose here we have a sun. Clear? And let's suppose we have sun, and let's suppose we are talking about this is earth, and let's suppose here we have another planet. Clear? Now you know very well earth is actually revolving around this sun in an elliptical form, in an elliptical path. So I can say let's suppose the earth is revolving like this and this planet is revolving around this sun like this. Clear? Now it's just I draw here this diagram. So let's suppose I am assuming here distance between earth and sun, I am taking this is RE, or let's suppose I am taking here distance between this earth and planet is RP. Clear? Now in this question it is given there exists a planet that went around sun twice as fast as earth. It means I can say time taken by that planet to complete one revolution, it is half of time taken by earth. Yes or no? Because it is given here this planet is actually revolving around this sun, it is having twice as fast as this earth. Clear? So we can say time period relation we can write like this. Now our objective in this question, what would be orbital size as compared to that of earth? So according to Kepler's third law, actually you know very well Kepler provided here three laws related to planetary motion of a planetary motion. Clear? So if we talk about third law, according to third law we can say the square of a time period, it is directly proportional to cube of mean radius of that planet with the sun. Clear? It means I can write like this t, it is directly proportional to r to the power 3 by 2. Clear? So from here we can write like this t, we can say Tp divided by Te, this should be equal to Rp divided by Re, and power this is 3 by 2. Clear? So now I can say this value, that is Tp. Clear? So Tp value is given 1 by 2 Te, so I can write like this 1 by 2 Te divided by Te, and this should be equal to Rp divided by, now we can say distance between sun and earth. Distance between sun and earth, this is actually known as 1 astronomical unit. Clear? So I am saying this is 1 astronomical unit and it is power 3 by 2. Clear? So from here I can write like this one and this one cancelled out, and from here you can see Rp, this is given by 1 upon 2 to the power 2 by 3. Clear? 1 upon 2 to the power 2 by 3 and multiplied with 1 AU, astronomical unit. Clear? So from here we can see this Rp, it is equal to, if you solve it you will find approximately 0.63 and astronomical unit. Clear? Definitely you should know what is value of 1 astronomical unit. So now you can see like this we can calculate orbital size of that planet with respect to Earth. So definitely you can say actually this planet is not at this place, this planet is actually here. Clear? And this is revolving around sun like this. Clear to everyone? So this is all about this question. Now student, we are going to discuss question number 8.4, and in this question it is given to you I naught, one of the satellite of a Jupiter, has an orbital period and radius of orbit that is given to you. Clear? So I can say let's suppose I am saying this is a Jupiter, let's suppose this is Jupiter, and let's suppose I am saying here this is one of a satellite. Clear? One of its satellite. Clear? And it is revolving around this Jupiter. Clear? In this question it is given to you, it is having orbital period. Orbital period means I can say time period, this is given 1.769 days. Clear? So can we convert this days into seconds? Yes. So I can say if we convert this time period in terms of a time period of a Earth. Clear? So in one day we have 24 hours and we have 3600 seconds. Clear to you? So now this is a time period in second. Clear to you? Now it is also given here radius of orbit. Clear? So I can say radius of orbit, this one is given by 4.22 into 10 to the power 8 meter. Clear? So radius of orbit, this is given to you 4.22 into 10 to the power 8 meter. Clear? Now we have to show that the mass of Jupiter is about 1000 of that of a sun. Clear? So how can we write? Actually we can write here one formula, that time period of an orbit, time period of a satellite, that is given by one formula 2 pi under root of r cube divided by gm. Clear? Now whenever we are talking about time period of this satellite of a Jupiter, at that time I can say here we will take into the consideration of mass of Jupiter. Clear? So from here if we square both sides, I can say this is t square 4 pi square r cube divided by gm. Clear? So now from here we can write like this, mass of Jupiter. Clear? I can say mass of Jupiter, this is given by mass of Jupiter 4 pi square, we can say this one we have r cube. Clear? Mass of Jupiter, this is given by 4 pi square r cube divided by gt square. Clear to you? Now if we talk about Earth and Sun. Clear? So let's suppose we can say here, let's suppose this is a sun and definitely Earth is a planet and this is revolving around this sun. Clear? So now we know very well time period is given by, this is equal to 365.25 days. 365.25 days. Clear? And if we convert into second, we can write like this. This is in second. Clear? And distance between Earth and Sun, this is given to you. Distance between Earth and Sun, this is given to you 1.5 into 10 to the power 11 meter. Clear? So distance between Earth and Sun, this is given 1.5 into 10 to the power 11 meter. Clear? So we can calculate here mass of a sun. Clear? Mass of a sun, this is given by 4 pi square. We can say this is r cube divided by gt square. Now listen carefully. If we take here ratio of mg divided by ms. Now listen carefully. This 4 pi square is a constant, it will be cancelled out. First we can write here r cube. So directly we can say distance. So 4.22 into 10 to the power 8 cube divided by, I can say value of we can say okay, divided by G, G will be also cancelled out, clear. So first we will write here time period square. So time period is given 1.769 into, I can say 24 into 60 into 60, and this one is whole square, clear. It is multiplied with, clear. Now we can say actually we are writing here ms in denominator, so definitely the RQ part will come in denominator and this t square goes to numerator, clear. So t value is given, so first I am writing here 365.25 into 24 into 60 into 60, and I can say this is square, divided by, clear, divided by we can say distance is given 1.5 into 10 to the power 11 whole cube, clear to you. Now if you simplify it, definitely here you can get your answer, clear. So now listen carefully. So a simple part we have, definitely calculation part is lengthy here, but definitely we can take here some approximation and we can find a conclusion that this mass of a Jupiter, this is almost 1/1000 times of mass of Sun, clear to you. Yes. So now concentrate. Now we can write like this, mg divided by ms, this is given by, clear. Now first try to cancel as much as you can. This is 10 to the power 24, this is 10 to the power 23. It means I can say this is 33 and this is 24. So 24, we can say here we will find 10 to the power 9, clear. So we can write like this 4 point, just a minute. Yes. So here we will find this is 4.22 whole cube, clear. 4.22 whole cube divide by 1.769 whole square multiply, clear. And actually we already write here this is 24 and this one we have 33, so 1/10 to the power 9 multiply, clear. Now you can say 24, 60 and 60 whole square, it will be cancelled out. So finally you can write like this, this is 365.25 whole square divided by, clear. I can say this is 1.769 whole square, 1.769 whole square, clear. So dear student, if you solve it, clear, approximation you can take here and you can solve it, easily solve it, clear. You can write like this, mj by ms equal to, let's suppose I am assuming this is 4.5 and this is, let's suppose 1.5, or you can take here, let's suppose if we are increasing this one, we have to increase this one also. So let's suppose I am saying this is 4, clear, and let's suppose this is 1.5, clear. So at that time you can say 4 into 4 into 4 divide by 1.5 into 1.5 into 1.5, clear, and multiply into 10 to the power 9, clear. I can say 365, so multiplied with 365 multiply 365, approximate we can say 1.5 into 1.5, clear to you, clear. Yes. Okay, actually here we have, this is cube and this one cube, here we will write 1.5, clear. So there is one mistake here, this one, clear. Here we will write 1.5, clear. 1.5 whole cube we have, so we can write like this is 1.5, clear. So we can write like this 1.5 and here we have cube, clear. So if you solve it, clear, approximate you will find here this value, just calculation is here, you can write like this is approximately equal to 1000, clear. So from here we can say mj, this is given by 1/1000 and times of mass of Sun, clear. It means we can say from here we can analyze that mass of a Jupiter, it is 1000 times of mass of a Sun, clear. So this is all about this question. Definitely this question is calculative one, but if you can take some approximation, you can easily solve this question, clear to you. So definitely in gravitation most of time you will find a lengthy calculations, but definitely you can take some approximation and you can reach near about result, clear. So this is all about this question. Now dear student, we are going to discuss question number 8.5, and in this question it is given to you, let us assume that our galaxy consists of 2.5 into 10 to the power 11 stars, each of one solar mass. Clear? So now we can say what is total mass of a galaxy. Clear? Total number of stars in a galaxy, this is given to you 2.5 into 10 to the power 11. Clear? And it is multiplied with one solar mass. Clear? So one solar mass, this is equal to 2 into 10 to the power 30 kg. Clear? So from here we can write like this, 5 into 10 to the power 41 kilogram. Clear? So this is a mass of a total mass of this galaxy. Clear? Now we can say, how long will a star at a distance of 50,000 light year? Clear? So it means we can say our objective here is to calculate time period. Clear? So now we can write here orbital radius, this is given to you 50,000 light year. Clear? 50,000 light year. Now 1 light year, this is equal to what? Clear? Do you know what is value of 1 light year? Yes, this is 9.46 into 10 to the power 15 meter. Clear? So now from here if you write, you can take this is approximate 9.5. Clear? So I can write like this, 5 into 9.5 into, this is 10 to the power 4, this is 10 to the power 15, I can say this is 10 to the power 19 meter. Clear? So if you multiply, you will find this is 47.5. Yes or no? So 47.5 multiply 10 to the power 19 meter. Clear? Yes. Now from here we can say our objective in this question is to calculate time period. So time period capital T. This capital T is given by 2 pi under root of r cube divided by gm. Clear? Capital T, this is given by 2 pi under root of r cube divided by gm. Clear? So now from here first I am squaring both sides. I can say this is 4 pi square r cube divided by gm. Now we can put here all the values. Definitely calculation will be more, and definitely tedious calculation we have, but we have to do some calculation. So 4 into pi square approximately I am taking, this is 10. Clear? Value of r this is given 47.5 plus 47.5 into 47.5 multiply, this is 10 to the power 19. So we can say this is 10 to the power 57. Clear? And it is divided by, now value of capital G. Capital G is universal gravitational constant, and this is 6.67 into 10 to the power minus 11. Clear? And what is mass? Clear? So now we can say mass is given 5 into 10 to the power 41. Clear? Now from here we can say this is 10 to the power 30. Clear? And if we cancel it, clear? So 10 to the power 30 and this is cancelled out, this is 58. So 30, 58, 10 to the power 28. Clear? This is 10 to the power 28. Clear? Now we have to take some approximation, because if you want to solve it. Clear? So approximately you can say this one is this one. We know this is 0.8, but we are approximately cancelling each other, and this is 6.6. So let's suppose I am assuming this is 7. Clear? So approximately I am saying, let's suppose this is 7 and let's suppose this is 49. Clear? So we can say this is 7 and let's suppose we are taking this also 49. Just an approximation, I am taking 49. So I can say 7 into 49 into 49 into 10 to the power 28. Clear? So now you can write like this. This is what? 50 minus 1, 50 minus 1. Clear? So we can easily calculate this one. Yes, definitely, because calculation is tedious, we have to take some approximations and we will find here nearby results. Clear? Yes. So now from here you can see we can write like this, value of time period t. Clear? Actually this is value for time square. Clear? So time square, this is given to you 7 into, I can write like this is 50 minus 1 whole square multiply 10 to the power 28. Clear? So 7 multiply, I can say this is 2500 plus 1 minus, I can say this is 100 into 10 to the power 28. Clear? So we can say I am not adding here 1 and directly we can say this is 2400. So 7 into 2400 into 10 to the power 28. Clear? So now we can say if you multiplied it, here we have 28, we have 2, so this is 100 into 10 to the power 28. Clear? So from here we are taking this is 168 into 10 to the power 30. Clear? So now if I take here square root, now we can see 169. 169 is approximately equal to 169 having square root 13. Clear? So we can see this value we have 13 into 10 to the power 50. Clear? So I can say this value we are getting in second. Clear? So clear? So this is answer of our question. Now it means we can see here what is total time taken by this star to complete one revolution. This is same. Clear? Now you can convert this time period into years or days also. Clear? Now we can say, let's suppose if we want to convert into years, first of all we have to divide by the number of days, 365.25, then we have to multiply it with 24, then 60 and then 60. So first we divide this expression with 365.25, then by 24, then 3600. After that we will get here answer in years. Clear? But if you want to keep this answer in only in second, this is a perfect answer. So nearby you can say we are getting this much amount of time period. Clear? So this is all about this question. Now we are going to solve question number 8.6, and in this question it is given to you, choose the correct alternative. Clear? In the first part it is given, if we are taking zero of potential energy at infinity. Clear? Then we have to find what is total energy of an orbiting satellite. It is negative of its kinetic energy or potential energy. So a very simple question we have, do you know that expression of a gravitational potential energy is given by GMEM upon RE. Clear? Now if I am talking about kinetic energy is given by half of mv square. Here m is what? That is mass of a satellite. So we can write like this, 1 by 2 capital M, and v is what? This is orbital velocity, and this is given by under root of gm upon re. So I can say this is under root of gme upon re whole square. Clear? So from here I can write like this, kinetic energy, and this one is given by 1 by 2 m, and this is gme divided by re. Clear? So from here we can see expression of a kinetic energy, this one is given by gme over twice of re. Clear? So if I am talking about total energy, clear? So total energy it is given by potential energy plus kinetic energy. So directly we can say this is gmem upon re plus, I can say this is gmem upon twice of re. Clear? So if you take here LCM twice re, then we can write like this, total energy, this one we have minus gmem divided by twice of re. Clear? So from here you can say, if I am talking about this statement, total energy of an orbiting satellite, it is negative of we can say kinetic energy of an orbiting satellite. Clear? So I can write like this, total energy equal to minus times of kinetic energy. Clear? So correct answer we have, this is negative of kinetic. Clear to you? Yes. Now if I am talking about part number B, the energy required to launch an orbiting satellite out of a Earth gravitational influence is more or less than the energy required to project a stationary object at the same height. Clear? Now listen carefully. Let's suppose here we have Earth. Let's suppose I am assuming this is Earth. Let's suppose we have a satellite at this position. Clear? So we can say definitely it is situated at a certain height. Let's suppose h. Clear? So at this time we can say, let's suppose this is stationary. So when this is stationary, actually we will provide here some velocity, and that velocity is known as escape velocity. Clear? Only. Clear? But important part is here, when this satellite is actually revolving in an orbit. Clear? So definitely it is also having some tangential velocity. Clear? It means I can say here at centripetal force will act towards the center and along radius. Clear? So let's suppose if we want to send this satellite out of gravitational field, first of all we have to overcome this centripetal force also. Yes or no? Yes. So we can say actually we have to provide more energy. We have to provide more energy when this satellite is having certain velocity and we want to we want to send this satellite out of a gravitational field. Clear? So definitely our answer is what? Definitely energy required to launch an orbiting satellite out of Earth gravitational field is more than the energy required to project a stationary object. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 8.7. In this question it is given to you, does the escape speed of a body from Earth depends on number 1 mass of a body. Clear? So actually we know expression of escape velocity, this is given by under root of twice g me upon re. Clear? So in this expression you can see here we are just getting mass of a Earth. It means here we are considering here only that mass from where object is projecting or object is giving certain velocity. Clear? So that it may move out from the gravitational field. Clear? It means here we will not take the mass of a body into consideration, we will take only mass of a planet through which that object is actually projecting. Clear to you? So definitely we can say escape speed of a body from the Earth depends on mass of a body? No. Clear? So directly we can say it does not depends on a mass of a body. Clear? Second, it depends on a location from where it is projected. I can say yes. Clear? Why yes? Because let's suppose I am saying here, let's suppose this is Earth. Clear? And when we have object at this position, I can say escape velocity we have, that is we can see this is given by under root of twice g me upon re. Clear? Where we can say re is the radius of this Earth and mass is given to you me. Clear? Now let's suppose a particle is already situated at this position. Clear? And from here it is having certain height, that is h. Clear? So if I write here expression of velocity. Clear? So expression of velocity we can say this is given by twice g me upon, I can say this is re plus h. Clear? So escape speed this is given by under root of twice g me upon re plus h. Clear? So definitely it depends on a location, I can say yes. Clear? So first here I am going to solve part number D, the height of location from where the body is launched. Yes, definitely, because the escape velocity is actually depending on the height also. More the height we have, the less velocity, less escape speed we have to provide that object or a satellite, so that it may out from the gravitational field of Earth. Clear? So from here we can say yes. If I am talking about part D, so definitely we can say it also depends on the height of location. Clear? Now last one we have part number C, it is depend on direction of projection. No. Clear? Let's suppose we are throwing an object at a vertical upward direction. Clear? And let's suppose we are throwing same object or we are sending that object at a certain angle to the surface of Earth. At that time we will find same expression of velocity, because here we are not getting any value that is related to angle. Clear? So I can see in part number C we have no. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.8, and in this question it is given to you a comet orbits the sun in an highly elliptical orbit. Clear? So let's suppose I am saying to you, let's suppose here we have, let's suppose this is a position of a sun. Clear? And let's suppose I am saying this is comet. Clear? And it is given in a question, this comet is actually revolving around this sun in an elliptical orbit. So let's suppose like this. Clear to you? Now we can say, let's suppose this is line joining between sun and this comet, and let's suppose I am saying this is r. Clear? Now in this question it is given, does the comet have a constant number 1 linear speed? Clear? So linear speed means we can say definitely this comet is going with certain velocity v. Clear? Now we know if we are talking about this point, and let's suppose if I am talking about this point. Clear? So one point is very near or nearest to this sun. Clear? And we can say this point is actually far away from the position of a sun. Clear? Actually we can say all planets revolve around a sun, and sun is situated at one of the focus. Clear? So let's suppose this is position of a focus, this is not a center. Clear? So at that time I can say here we have one position. So at this position, when this comet is near to this sun, definitely its speed will be more compared to this position. Clear? It means we can say at each and every point velocity of comet is changing. That's why we can say if we are just talking about linear speed, this linear speed not remain constant. Clear? So I can say answer of part number A we have, this is no. Clear? It means I can say linear speed or linear velocity, it will not remain constant. Clear? Actually, if we are talking about velocity, the direction of velocity at each and every point is changing. Clear? So that is entirely different. Clear? But if we are talking about linear speed, so we can say here magnitude of velocity, that is also changing. Clear? That's why we can say linear speed, it will not remain constant. Clear? Now if we are talking about angular speed, clear? So definitely we can say angular speed, it will also changes. Clear? Angular speed is also changes, and we can say yes, definitely this value we have no. Clear? Now if I am talking about part number C, so in part number C it is given to you angular momentum. Clear? So always keep in mind, whenever any planet or any comet that is revolving around sun, at that time we can say total angular momentum always remains conserved. This is one of the this is actually one of the good question that may be asked from here. Whenever a planet is revolving around sun in an elliptical orbit, which physical quantity remains conserved? That is we can say angular momentum. Clear? You can see like this. Actually angular momentum, this one is given by m r cross v. Clear? m r cross v. So you will find at every position angle between this r and v vector we have always, that is actually we are talking about this is L, this is equal to m r cross v. Clear? R is given to you in this position. Clear? And here we have v. Clear? So if we are talking about this physical quantity, this physical quantity always remains conserved. Clear? Because we can say for a particular point we have constant r, we have constant v. Clear? And we can see if we are talking about L. Clear? So angular momentum, that is we can say, we can write like this m1 r1 and we can say v1, m1 v1 r1, this should be equal to m2 v2 r2. Clear to everyone? So now we can say magnitude wise it will remain same. And what about the direction of angular momentum? Direction of angular momentum will always, we will find that is r cross v. We can say this is r vector. Clear? And this is v. So we can say if we curl our finger from r to v, clear, it will give you the direction of angular momentum, and the direction is given by this perpendicular to this screen. Clear? So question we have that whenever a comet is revolving around sun in an elliptical orbit, angular momentum is conserved? Yes, definitely angular momentum conserved. Clear? Now if I am talking about part number D, clear? So in part number D it is given to you what about kinetic energy. Now you can say kinetic energy is given by half of mv square. Clear? And we can say value of v is changing. Clear? It means magnitude of velocity is changing. So I can say definitely kinetic energy, it will also changes. Clear? So our objective in this question is to find constant quantity. So I can say definitely kinetic energy, it will not remain conserved, or we can say kinetic energy also changes from point to point. Clear? So this is all about part D. Now if I am talking about number E, potential energy. So we can say with the time position of a comet with respect to sun is changing. Clear? So definitely I can say yes, potential energy is also changing. So we can say potential energy also not remain constant. Clear? Now what about total energy? Clear? What about total energy? So always keep in mind, whenever a comet is actually revolving around sun, at the time we can say total energy is given by sum of kinetic energy and potential energy. Definitely we can say when potential energy decreases, at the same time kinetic energy increases, or when kinetic energy decreases we can say potential energy increases. It means I can say if we are talking about total energy, so total energy, it always remains constant. Yes, I can say it always remains constant. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.9, and in this question it is given to you which of the following symptoms is likely to affect an astronaut in space. Clear? So whenever an astronaut remain in a space, what type of problem they face? Definitely we can say orientation problem they are facing, because there is a absence of gravity they have. So definitely we can say yes, orientation problem they have. Clear? It means we can say D part is correct. Clear? And definitely we can say headache. This problem will they also suffer, that is headache, as well as their face actually swallow. Clear? It means we can say this part is also correct. Clear? So this is the three problems that you can say yes, feet will not swallow. So this is a theoretical type question, a very simple theoretical type question. We cannot do something new here. So directly you should keep in mind, correct answer we have B, C and D. Clear to everyone? So this is all about this question. Now we are going to discuss question number 8.10, and in this question it is given to you, choose the correct answer from among the given ones. Clear? The gravitational intensity at center of hemispherical shell of uniform mass density has the direction indicated by arrow. Clear? So let's suppose if we are saying, let's suppose here we have this hemisphere. Clear? And we can say, let's suppose this C is denoting center of this hemisphere. Clear? Now if I am talking about the direction, exactly what will be direction of gravitational intensity. Clear? So our objective here is to calculate direction of E. We can say gravitational intensity, you can say this is gravitational field. Clear? So now concentrate here. Let's suppose if I take here a very small element, listen carefully what I am saying to you. Let's suppose I am taking this as small element. Clear? And now we can say, due to this small element we will find direction of gravitational intensity. Direction of gravitational intensity in this direction. Clear to you? Similarly, if you take here a small element this side, you will find gravitational intensity in this side. Yes or no? Clear? So let's suppose if I take here a very small element like this. Clear? So value of electric field, what we can say, direction of electric field you are getting in this direction. Clear? Now you can say, actually if you are talking about B and C, this is given to you like this, but actual mein it is like this. Let's suppose this is a point, this one is a point. Clear? So I am saying here this direction indicating C, this direction indicating B. So definitely we can say, if I say here this is the half part of hemisphere, so electric field due to this half part, it will be cancelled out by electric field due to this half part. Clear? It means we can say B and C is not the correct answer. Now we have only two options. Clear? So now we can say, if we are talking about all the directions, now you can say horizontal component will be cancelled out. Clear? And we will find net resultant intensity in the downward direction. Clear? So correctly we can say here that the direction of electric field intensity, it will be indicated by C. Clear to you? So this is all about this question. Now student, we are going to discuss next question, question number 8.11, and in this question it is given to you, the direction of gravitational intensity at an arbitrary point capital P is indicated by the arrow. Clear? And now we here have four options, D, E, F and G. Clear? Now let us try to understand. Let's suppose I am taking here a point P. Clear? And this point P is not lying in a center. Clear? So again you can say, if you are talking about, if you are taking here a very small element, let's suppose this one, so definitely direction of gravitational field in this direction. Clear? If you are taking any element, let's suppose if you are taking here this element. Clear? Definitely we can say electric field, the direction of electric field due to this element in this direction. Clear? My objective in this question is to find the direction of resultant gravitational intensity. Clear? So definitely we can say here we will find direction in the direction of electric field in the direction of E. Clear? Definitely we can say D and G is cancelled out, and correct answer we have part number 2. So in different books you will find different solution, but directly and logically you can say here directly what is direction of electric field. Clear? So this is all about this question. We are going to discuss question number 8.12, and question is given to you, a rocket is fired from the earth towards the sun. Clear? So let's suppose I am taking this is earth. Let's suppose I am taking this is earth. Clear? And let's suppose I am saying this is sun. Let's suppose this is sun. Clear? In this question it is given a rocket is fired from earth towards sun. So let's suppose I am saying this is a line joining center to center of earth and sun. Let's suppose, for example, I am actually firing a rocket from this point. Clear? I am firing here a rocket from this point A and I am firing this side. Clear? Because I am actually firing rocket from earth to sun. Fine. So now we have to find at what distance from earth center is the gravitational force on rocket is 0. Clear? So let's suppose for some time, let's suppose this rocket move up to this point. Clear? I am saying this point is B. Clear? And let's suppose I can say this point is O. Clear? And let's suppose this point is O dash. Clear? So let's suppose at point B I am assuming net force acting on this rocket becomes 0. So how can net force become 0? Clear? So let's suppose I am taking mass of rocket. Clear? So mass of rocket I am taking, this is small m. Clear? I am taking mass of earth, this is equal to me. Clear? And mass of sun I am taking, this is ms. Clear? Now let's suppose if I am taking distance between center to center and this is given by, let's suppose this is r. Clear? And actually this value of r, this is given to you 1.5 into 10 to the power 11 meter. Actually we know what is distance between earth and sun. Earth and sun we have distance this much amount. Clear? Now let's suppose I am saying from the center of a earth we are getting net gravitational force 0 at position x. Clear? Or we can say at position B at a distance x from center of earth. Clear? So now we can say, how can we say here net gravitational force is becoming 0? Clear? So now concentrate. First of all, if I am concentrating on a sun, definitely sun will exert a gravitational force. Sun will exert a gravitational force towards center along radius. Clear? Same here we can say at point B, earth is also exerting a force towards center along radius. Clear? So definitely we can say on the rocket two forces are acting by two different planets, we can say. So now we can say here, let's suppose we already assumed here that net force is 0. So I can write like this, Fs, this should be equal to Fe. Now can we write here formulas? Yes. So now what is formula of Coulomb's law of Newton's law of gravitation? Clear? Here we can say what is formula of Newton's law of gravitation. Directly we can say this is G, ms, let's suppose this is m, and we can say what is distance between sun and this point, definitely r minus x. So r minus x whole square, we can write like this, this is g me m divided by, we can say this value we have x square. Clear? So we can say here g and g, this is cancelled out, m and m, this is also cancelled out. Clear? So we can say here mass of our objective is what? We have to find value of x. Clear? So we can write like this, we can say r minus x divided by x whole square, this is given by ms divided by me. Clear? So now we can say r minus x divided by x, this is given by under root of ms over under root of me. Clear? So r minus x upon x, this is given by under root of ms upon under root of me. Clear? So r minus x divided by x, this is given by under root of ms. Ms means we can say mass of a sun. So mass of a sun, you know, this is 2 into 10 to the power 30. Clear? And what is mass of earth? Mass of earth is given to you 6 into 10 to the power 24. 6 into 10 to the power 24. So from here we can say this value we have, that is 3, and we can say this is 6. So we can write like this, r minus x upon x, this is equal to 10 to the power 6. 10 to the power 6, if I take square root, I can say this is 10 to the power 3 divided by under root of 3. Clear to you? So from here you can say, we can write like this, what is value of 1000 divided by under root 3? Clear? 1000 divided by under root 3, I am taking this value equal to 577.35. 577.35, you can easily calculate. How? You can say, let's suppose I am taking 1000, this is 1.75. So you can actually 1.73, you can write, let's suppose this is 5 by 3. Yes or no? Yes, we can say 5 by 3, 315, 36. No, we can say here this is 1.75. 1.75 means we can say 5 whatever. So we can say this is 1.75. So 1000 divided by 1.75. So approximately you will get here, that is 577.35. So from here we can write like this, r minus x, this is equal to 577.35 times of x. Clear? So now if you take this x to the right side, finally you can write like this, r, this is given by 578.35 x. Clear? Now my objective here is to calculate value of x. So x, this is given by value of r, it is already given to you, this is 1.5 into 10 to the power 11. So 1.5 into 10 to the power 11 divided by 578.35. Clear? So now you can say if we multiply it with 1000, we can say this is 1500. Clear? So approximately you are getting near about 3. Yes or no? So directly I am saying here you are getting value 2.59. Clear? Multiply. Now you can say actually you multiplied with 10,000. So we can say here we are getting 10 to the power 8. Clear? So value of x that we are getting 2.59 into 10 to the power 8, and I can say this is meter. Clear? So what is the conclusion or what is the result in this question we have? Conclusion is very simple. This rocket, this we can say net force that is acting on this rocket is 0 at a distance 2.59 into 10 to the power 8 meter from earth. Clear? So this is all about this question. So now student, we are going to discuss question number 8.13, and in this question it is given to you how you will weigh the sun, that is estimated its mass, the mean orbital radius of earth around the sun, this is given to you 1.5 into 10 to the power 8 kilometer. Clear? So now let us try to understand. Let's suppose I am saying this is a sun. Clear? And let's suppose here we have earth, and definitely we can say this earth is actually revolving around this sun in an elliptical path. Clear to you? But for calculation purpose we are assuming this is a circular path. Clear? Now we can say distance between sun and earth, this is given to you, that is small r. Clear? So value of small r, this is given to you 1.5 into 10 to the power 8 kilometer. Clear? So now from here we can write like this, 1.5 into 10 to the power 11 meter. Clear? Yes. Now my objective here is to calculate mass of a sun. Clear? So how can we calculate? So from here we can say if we write here time period. Clear? So let's suppose we are assuming a satellite is revolving around a planet. So time period of that satellite, it is given by t equal to 2 pi under root of r cube divided by capital GM. Clear to you? So now from here what is my objective? My objective here is to calculate value of m. So I can write like this, this is t square, this is equal to 4 pi square multiply r cube divided by, I can say g, and here we are writing mass, that is mass of a sun. Clear? So from here we can write like this, mass of sun, this one is given by 4 pi square multiply r cube divided by gt square. Clear? So now we can say mass of sun. Clear? So value we have 4 pi square, approximately we are taking this is equal to 10. Clear? Multiply r cube. R is what? This is we can say r is what? This r is distance between earth and sun. Clear? And this value is given to you 1.5 into 10 to the power 8 kilometer. Clear? So 1.5 into 10 to the power 11, and we can say this power cube. Clear? Divided by g. Clear? G we have 6.67 into 10 to the power minus 11 multiply. Now we can say time period. Clear? So now we know earth revolve around sun in 365.25 days. So we can write like this, this is 365.25, this is number of days. Clear? So now we can say in one day we have 24 hours. Clear? And we can multiply here with 3600. Clear? So now from here we can write like this, mass of sun, this is given by 40 into 1.5 multiply 1.5 multiply 1.5 into 10 to the power 33. Clear? Divided by 6.67 into 365.25 multiply 24 multiply 36 into 10 to the power minus 9. Clear? So now from here if you calculate it, clear, at the time you can find here mass of a sun. Clear? So if you calculate, we can say this value you will find approximately equal to 2 into 10 to the power 30 kilogram. Clear? 2 into 10 to the power 30 kilogram. Clear? So mass of sun is given by this value, and this is actually known as one solar mass. Clear? This is also known as one solar mass. Clear? So this is all about this question.